Okay, ladies and gentlemen, you are welcome. In today's lecture, we are going to look at physics 122, specifically electrostatic. So I think if you could remember last time in some of my videos, we discussed on the concept of electrostatic, which defined as the study of electrical charges at rest. So in this video today, we are going to look at the concept of capacitor. Capacitor. So what is a capacitor? A capacitor is an instrument that you use for storing an electrical charge, or is a device that you use for storing electrical charge. It's a device used for storing electrical charge. That is what we call a capacitor. So it's a device that we use in storing an electrical charge. And of course, apart from a capacitor, we have what we call a capacitance. We have what we call capacitance. Capacitance. So capacitor is a device that you use for storing an electrical charge, while capacitance is different. So a capacitance is like a process. So therefore a capacitance is defined as the ability of capacitor to store electrical charges. That is what we call a capacitance. So a capacitance is the ability of a capacitor to store an electrical charge. So first we start with a capacitor. So a capacitor is a device that used for storing an electrical charge, while a capacitance is the ability of a capacitor to store an electrical charge. And very importantly, we should know that, ladies and gentlemen, these charges that we are talking about is represented as Q. So Q can be considered as a quantity of electrical charge. Quantity of electrical charge. But this quantity of electrical charge is dependent on the amount of the voltage. So the quantity of the electrical charge stored by a capacitor depends on the amount of the voltage. So that is why there is a direct relationship between the quantity of electrical charge and the capacitor. So that is why capacitance is directly proportional to the voltage. So the quantity of the electrical charge is directly proportional to the voltage applied to the circuits, indicating that if the quantity of electrical charge increases, or if the amount of the voltage increases, it means that the quantity of the electrical charge will also increase. So remember, ladies and gentlemen, wherever there is proportionality, we introduce constant. This implies that we now have Q is equal to CV. The C here stands for capacitance. It stands for capacitance. While the V here stands for voltage. It stands for voltage. So this V here stands for voltage. And then the Q here, of course, is the quantity of electrical charge. So from here, we can make C subject of the formula. We have CV. So therefore, we can divide it through by V, and this one can also be divided by V. So therefore, this V will now cancel V, And at the end, we now have capacitor is equal to Q all over V. The Q is measured in column, while V stands for volt. So therefore, the capacitor can be measured as column per volt. Or if you check another, okay, you can measure it as either column per volt or farad. So this is the units that is used in measuring the capacitance of a capacitor. So ladies and gentlemen, it is very important to know that there is what you call a capacitance of a parallel or capacitance of a parallel plate. We have what you call capacitance of a parallel plate, and that is what we are going to look at now. So what is, or before then, we can also calculate the energy, or we can also drive the formula, or we can get the formula for calculating energy stored in a capacitor. So at the same time, ladies and gentlemen, you can also measure or you can also calculate the energy stored in a capacitor. So the formula for calculating energy, so energy stored in a capacitor is equal to 1 all over 2 CV squared. Or at the same time, remember here, we can also use energy stored in a capacitor. It can be 1 all over QV. And also at the same time, from here you can manipulate this Q. You know that Q is equal to IT. So energy stored in a capacitor can be related as ITV. So all these are the formula for calculating energy stored in any capacitor. Is that clear, ladies and gentlemen? So I want to actually bring all the formula out, then we now take some questions and solve them. So we also have, apart from, so capacitance of a parallel plates capacitor can be given by a formula as capacitor is equal to A epsilon naught all over D. So that is why if you also want to know the factors that affect the capacitance of a capacitor, we have them. Number one, if there is an increase in a distance of separation between two plates, generally sometimes you have a capacitor like this. You have plate 1 and you have plates 2. And there is a distance of separation between them, that is D. There is a distance of separation between them. So here, ladies and gentlemen, one of the factors that affect the capacitor of a parallel plate is the distance. So if there is an increase in a distance, ladies and gentlemen, let me just give you one hint in this physics. Sometimes you will be given or you will be asked a theory questions, but it is a formula that you will be used to solve the problem. It is what? A formula that you are going to use to solve the problem. Like for example, you may be asked what are the factors that affect the capacitance of a capacitor. So one of the factors is the distance of separation. So whenever there is an increase in the distance of separation between two plates, so therefore the capacitance will decrease. And when there is an increase in the area of the plates, so there will be an increase in the capacitance. So you should understand that between the capacitance and the area, there are direct relationships. So if one increases, then the other one will decrease. And if you now you have the distance of separation. So if there is an increase in the distance of separation, so definitely the capacitance will be decreased. So this is what we call capacitance of a capacitor, and this is some of the formula that we are going to use in the calculation of the capacitor. So we have capacitance. The formula for calculating capacitance is Q1 over V. And we have formula for calculating energy stored in a capacitor, where you have energy is equal to half CV square, and you have E is equal to half QV, or E is equal to half ITV. So these are the formula that I use in calculating capacitance of a capacitor. So after this, ladies and gentlemen, we also have the arrangement of a capacitor. Arrangement of a capacitor. Arrangement. Arrangement of a capacitor. So capacitor can be arranged in different ways. It can be arranged in parallel. We have parallel arrangement. So let's look at the parallel arrangement of a capacitor, the parallel arrangement of the capacitor, and also the arrangement of a capacitor in series. That is what we are going to look at first. Let me get the diagram because I want to show you how these capacitance are arranged diagrammatically, so that at least whenever you see them, you will know that the kind of the arrangement. So the arrangement of the capacitors, that is what we are going to look at. So when you say parallel, ladies and gentlemen, it means that you have a capacitor, one is parallel to another. And you have also arrangement of a capacitor in series. Arrangement of a capacitor in series. So you can have a plate like this, where you can have, okay. Yeah, because the diagram is also very important in calculating some of these things. Okay, so now let's look at this. You can have a plate like this. So I want you to really feel very well. So you can have a capacitor like this. So these are the different capacitors. Let's say C1 here. Let's say this one is C2 and this one is C3. So as you can see clearly, ladies and gentlemen, from here, this is a parallel capacitor. So if you can see, P1 is parallel to C2, C2 is parallel to C3. So the arrangement of a capacitor in series and in parallel, so the parallel arrangement of capacitor is given as C1 or C effective, you can call it C effective, is equal to C1 plus C2 plus C3. So depend on the number of the capacitor. Let's say you have 10 capacitors. So it's going to be C1, C2, C3 plus C up to C10. So that is the arrangement of capacitor in parallel. So the next thing is arrangement of a capacitor in series. So sometimes you'll only be given the diagram. So from the diagram, you'll use the diagram from there to know whether your capacitor is in series or in parallel. Like for example, now if you have something like this, you can have a capacitor like this. I think it is clear, ladies and gentlemen, you are seeing it. So you have a capacitor like this. So you see this one and this one, they are in series. And this one, they are in parallel. So therefore, we now have C1 here, C2, and C3. So the capacitor in series, we have a formula like this: 1 all over C effective is equal to 1 all over C1 plus 1 all over C2 plus 1 all over C3 plus dot plus 1 all over, depending on the number of the capacitor. If you have 10 capacitors, so you arrange them like that. If you have more than 20, you arrange them in series like this. So capacitor in series is always in a reciprocal form. So 1 over C1, 1 over C2 plus 1 over C3 plus 1 over C3 plus 1 over C4. That is the arrangement of the capacitor in series. And then the arrangement of the capacitor in parallel is like this. So ladies and gentlemen, without wasting much of our time, we are now going to look at examples and solve. Let's start with this example. Calculate the capacitance of an empty parallel plate capacitor with a metal plate with an area of 1.00 meters square separated by 1.00 millimolar. Sorry, not millimolar, milliliter. Millimeter. So we have 1 millimeter and we have area and we have to calculate the capacitance. So from here we can now see C is unknown. And the area here is given as 1.00 meters square. And then the distance, which is T here, is given as 1.00 millimeter. And milli, if we know that milli is the something as 10 power minus 3. So therefore we have 1.0 times 10 raised to the power of minus 3 meter. And then we have epsilon, of course, from this formula, because we are going to use a formula that says A is equal to A epsilon all over the distance. And of course, ladies and gentlemen, we know that epsilon is a constant value. Epsilon is a constant, which is the something as 8.85 times 10 raised to the power of minus 4. So epsilon naught is the something as 8.85 times 10 raised to the power of minus 12 farad. So the area here is given as 1.00 times 10, times epsilon, which is 8.85 times 10 raised to the power of minus 12. And then divide by the distance here is given as 1.0 times 10 raised to the power of minus 3. So 1.00 divided by 1.00 is something. So therefore it is only this one that will take this. So therefore remember from indices when we have 8.85, so we have times 10 raised to the power of minus 12. And in the indices, whenever you have a division, because this is a division, so you take this 10, it will, when it will take it to this side, so it's going to be at the end, we have minus already here. So this division in indices is the same thing as minus. So it already has its minus 3, it has negative value. So therefore it's going to be 8.85 times 10 raised to the power of minus 12 plus times minus times minus is plus. So therefore at the end we are going to have 8.85 times 10 raised to the power of minus 9 cos farad. Okay, this one is not farad. So we have 8.85 volts per meter. Let's use volts. Remember, we said that C is equal to Q all over V. So we have column for volts. So that is actually the answer to this. I think, ladies and gentlemen, this is very clear. So let's look at another example. Okay, ladies and gentlemen, I solved one. I solved one. I want you to try two and three. And please, after watching this video, you saw these questions. If you watch, work on this and put the answer on the comment section of this video. Because most of you, that is what you are doing that discourage me from doing videos. I solved this one and I want you, it's almost the same procedure. So solve 2 and 3 and put the answer on the comment section of this video. And if you do that, then we'll continue in the next video with the continuation of this. Thank you very much.